This lesson is for Advanced Algebra, Lesson 2-3 on the fundamental theorem of variation. Students have been learning this week about direct and inverse variation. And so both of those are involved in what we're going to do today with the fundamental theorem. The fundamental theorem is divided into two parts. One part related to direct variation, the other part related to inverse variation. I've divided the examples today into direct and inverse as well. So let's look at the first part of the fundamental theorem. If you have a direct situation and the x value or the independent variable gets multiplied by something, then the y value gets multiplied by that same value raised to any powers that may exist. So the n value here, or the power, has to match with the power that's on the x. Let's put that into practice with a specific example. Let's say you have this direct example, a equals 5w. We want to know what the effect on a would be when w is doubled. Remember that doubled simply means it's multiplied by 2. So let's make a quick table of values and see if we agree with what the fundamental theorem states. So if I have w as my independent variable and a as my dependent, let's just plug in some simple numbers like 1, 2, 3, and 4. If I plug 1 into the equation, I get a 5. If I plug 2 into the equation, I get 10. Plug 3 in, I get 15. Plug 4 in, I get 20. So now let's look at what happens if if w gets doubled. Let's start with this one. If I take that w and multiply it by 2, what happens to the w? The w turns into a 4. What is the effect then on the a value? The a value also got doubled. So that's how you would answer the question. What is the effect on a when w is doubled? A gets doubled. Or another way to say that is you could say a gets multiplied by 2. Let's see if that matches with what the fundamental theorem would say. If x, or in this case w, gets multiplied by 2, then y, or a, gets multiplied by 2 to the n. We didn't have an n, so it just stays as a regular 2. Let's try that again for a different amount. Let's say that the that the w gets tripled. So if we start with the first coordinate and multiply it by 3, the 1 turns into a 3. Let's see what happens to the a. The a goes from 5 to 15, so that gets multiplied by 3 as well. So we don't need to use the table any longer now that we know that we can trust what the fundamental theorem says. So when w is tripled, a gets tripled. Or another way to say it is, a gets multiplied by 3. Let's try another one with exponent involved and see how that affects our answer. For the next example, this time our equation is a equals pi r squared. What is the effect on a when r is doubled, or multiplied by 2? Let's utilize the theorem this time to answer the question. If r gets multiplied by 2, we know that this is a direct situation, so the a value should also get multiplied by 2, and then we just need to pay attention to any powers that exist. There is a power on the r, so that power has to get incorporated in our response. So since that's a square, we need to say square there. So now when we actually write our response in words, we'd say that a gets multiplied by 2 squared, or by 4. So you could say it either way there. I think I prefer 2 squared because it shows me that you know that the 2 has to be there, but that 2 gets raised to the power that's indicated on the r value. Notice that the pi here is uninvolved in what we're doing, and he just sits there. All we're worrying about is the two variables and how they relate to each other. Let's try it again now. What is the effect on the same equation when r is tripled? So if we multiply r by 3, that means since it's a direct situation that we're still going to multiply by 3, but we need to incorporate that power. So a gets multiplied by 3 squared, or by 9. For students that still aren't trusting that that is the correct answer, let's do a quick table just one more time. So we've got r and we've got a. Let's pretend that that pi value was simply a 1 just for the ease of calculation for now. We do 1, 2, 3, 4 again and fill in values for a. If we simply square the r, we get 1, 4, 9, 16. So let's see what happens when we double. So the 2 turns into a 4 when we double, but the y value, or the a value here, is not doubling, it's being multiplied by 2 squared, or 4. Let's see if the same is true when we deal with the tripling. When we go from 1 to 3, that's a triple, but the y value, or the a value here, is turned into a 9, so that's multiplied by 3 squared. So the whole point of the fundamental theorem is to eliminate students having to do this verification with the table and to simply trust what the theorem says. So those are your 2 direct examples. Here's your 2 inverse examples. The students should take a moment to copy those. Let's just quickly review the theorem before we try these 2. For the inverse part of the theorem, when x is multiplied, then the y value gets divided. We still have our c value, our number that we're using, and then the c value that has the result on the dependent variable has to get raised to the power that's included in the original. We just need to pay attention here when we're doing inverse. The words multiply and divide have to go together. So let's try our inverse examples. This time d gets doubled, or multiplied by 2. So that means the I value, since this is an inverse situation, has to get divided by 2. The only other thing we need to worry about here is if there's any powers on the d. It doesn't have any, so we're finished. So when d is doubled, I gets multiplied by 2. Divided by 2. It's very important that we do that for the inverse equation. It has to get divided by 2. If one's multiplied, the other one has to divide. Let's look at it for tripling. If we multiply this one by 3, then the I has to get divided by that same number. So for the tripling one, I gets divided by 3. Let's look at a situation where we have a power involved and see how that affects our answer. What is the effect on d when t is doubled? So if we take t and multiply it by 2, the d, since this is an inverse situation, has to get divided by 2, and then we need to incorporate that power. So we'd say 2 squared. So we'll say that d is divided by 2 squared, or we can say 4 there. If we do the tripling, multiplying it by 3 means that we're going to be dividing by 3 squared, or 9. So d is divided, since it's inverse, by 3 squared, or 9. So I'd like students to give this a try now. I'm going to give them a mixture of direct and inverse problems to try on their own. Before I have students try them, I just want to quickly review the steps that they want to take. The first thing you should do is decide if it's direct or inverse, because that will dictate how you're going to answer. The second thing you should do is then, based on that, decide if you're going to say multiply or divide. If you're working with a direct situation, just make sure if you're multiplying in the original, then the result has to get multiplied as well. If it's inverse, if you're multiplying here, then you have to divide in your answer. The last step is just to divide or figure out what you're going to use for your multiplication or your division. It's either going to be a c or a c to the n. If there is no n present, then you just simply use the same number again. If there is an exponent present on the original independent variable, you need to go ahead and incorporate that in your answer. So I'd like students to try these next 3. Technically they should be labeled A, B, C here instead of 6, 7, 8. So students should take a moment to try these on their own, and then I'll display the answer momentarily. So students should have found that the first one was direct, the other two were inverse. Since it's direct, multiplying here should turn into multiplying there. There is no power, so it's simply multiplied by 2. The next two are both inverse, so when we say multiply for the original, then the answer needs to be divided. There's no power on this one, so we just say divided by 3. There's a power on this one, so we need to say divided by 2 cubed or 8.